right? X is mapped to, right? X is mapped to T of X, right? Let me erase this part, right? X is mapped to T of X by the map T. X is taken to the image Tx by the map T. Similarly, Y is taken to the image T of Y, okay, by the map T. T takes Y to T of Y. This is T of Y. Right? T of Y. Okay. So T of X is an element in N dash. T of Y is an element in N dash. So these are elements in the codomain N dash. And this addition is the addition in this vector space N dash. So there is difference. Even though we write the same symbol, according to the context, we understand. X and Y are coming from N. Therefore, this is addition in N. And T of X, T of Y are coming from N dash. Therefore, this is the addition in this vector space N dash. Okay. There may be difference. If your spaces differ, if your domain and codomain differ, these two pluses differ. Okay. What this means is that the T image of sum of the vectors X plus Y is the same as the sum of the individual images. Means this function T retains. It's a kind of homomorphism. This function T retains addition. Okay. It is the T image of sum of vectors is sum of the individual T images. Okay. And here, the T image of the scalar product alpha times X is alpha times the scalar product T of X. Alpha times the vector T of X. Okay. This is the scalar multiplication in N. X is coming from N. Alpha is from field. So alpha dot X is coming from N. Okay, this is the scalar product multiplication in N. Here, T of X is an element in N dash. This alpha is multiplying this image. T of X is a vector in N dash. So here, the scalar multiplication is from N dash. Both these scalar multiplications may differ. If your spaces differ, these scalar multiplications, these two scalar multiplications differ. Okay, you should be careful. And what this means is that this T of the scalar product is the scalar product of the image by this for the same scalar. Okay, so in a way, T preserves the scalar product. Okay, so it's a kind of a homomorphism. T preserves both addition and scalar multiplication. If our map T is this kind of the addition preserving and scalar multiplication preserving map, we say that T is a linear map. Okay, or a linear transformation from the space N into the space N dash. Okay, that's what we mean by a linear transformation from a vector space N into a vector space N dash. Now, let us move to the boundedness property. Okay, right. So I want to talk about bounded linear maps. Okay, or bounded linear transformations. The question is, do we have maps, linear maps, which are not bounded? Okay. First, let us look at some simple examples of linear maps. Okay. So we want to give examples of linear maps. Okay. Right. So to give example of a linear map, you need to have one or two vector spaces. If you have one vector space, you can take N dash equal to N. Okay. Yeah. So let us look at this. Let us define T to be the map 0, which takes no, not here, not this 0. Here, you take any general element X from N. This should go to the 0 in N dash. N dash is a vector space, and 0 is additive identity. 0 is additive identity in N dash. So you take every element here X to 0. Okay, so my mapping is this. T of X is 0, is identically 0. Or in other words, T of X is defined as 0 for all X belonging to N. Okay, and this is called the 0 transformation. Why? This is the 0 transformation, 0 map, 0 linear map. Why is it 0? It is taking every element X to the image 0. Okay, It is a constant map. And because the image is 0, singleton 0, okay, the range is of this function, the range is singleton 0. The image of every x is the same singleton, same element 0. Okay, that's why we call this 0 map. This is a constant map. Okay, well, you can easily see that this is a linear map. How? T of x plus y. Let us look at this. T of x plus y. What is, is it equal to T of x plus T of y? Let us check. Okay, T of x plus y. If x and y are taken from n, right? I'll take x and y from n. I'll take y from here. So x plus y is an element in n because n is a vector space. I assume n and n dash are vector spaces for the same field f. Okay, so x plus y is in n and T of x plus y is defined to be 0. Okay, what will be x plus y? T value is 0. And this T value is also 0. This T value is 0. And in n dash, these are the 0 elements. Okay, and if you add 0 to 0, you get back. You get this sum also to be 0. Okay, sum of, right? This is the addition property. So this 0 is this 0 are same. That is how this is correct. T of x plus y is T of x and T of y for any x and y coming from n. Okay, let's look at the T of alpha times x, or the scalar T of scalar product c times x. Okay, you may take c also here in case of alpha. Okay, now the question is this equal to T of alpha times dx? This is the question. Okay, alpha x, this is a vector. Alpha is coming from field. Alpha is coming from field. So alpha x is a vector in n. Alpha is a scalar. Elements in field are called scalars. So alpha is coming from field and x is coming from n. And alpha x is, because n is a vector space, alpha x is an element in n. So t acts on n. So T of alpha x is well defined. Okay, and the image of any element is 0. This is 0. Okay, similarly, this T of x is also 0. Okay, for x, the T image is 0. For any element x, whether it is x or alpha x or x plus y or dy, every T image is 0. Okay, and if you multiply alpha, if you multiply 0 by alpha, you can show that the product is 0. Okay, that's how this also will be 0. That's how, and these two zeros are same. These are the zeros in the T in the image in the codomain. That is n dash. Okay, that's how, and these are the same zeros. Okay, and that's how we have equality here. Okay, that's how the linear map, the zero transformation is a linear map from the space n into any space n dash. Okay, this is a constant map, right? Yeah. Now let's end the point. Here, what is happening? What is image of this zero map? What is image? What is the range of this zero map? All elements 0 of x, because that x belongs to n. Okay, I am by R I mean the range. Okay, this is range, right? Yeah. So the range of the zero map is what? It is formed of the images 0x, where x varies over the domain set n. Okay, and 0 of x is 0. 0 of x is 0. Okay, what will be x? Right, and this x, this 0 is the 0 in the codomain n dash. Okay, and this in fact is singleton 0. This is 0 for any x value. 0 of x is 0. So a range is singleton 0. Okay, here, so we have a range of the 0 map is singleton 0. Okay, and we have 0 is defined from n to n dash over the same field. Okay, and then we can as well expect norm structure on each of these vector spaces. We may have different norms, okay, or same norms on these two vector spaces or linear spaces. So you can have, you may take norm structures on these vector spaces. Okay, so then you can speak of instead of 1 and 2, I hide these suffixes, because from the context we can understand whether we are taking norm 1 or norm 2. Okay, so let's look at the norm of this. Norm 0. Okay, and this 0 is the 0 in n dash. Okay, is n dash. So this is, I'm taking norm 2. Norm 0 is norm 2. Okay, I'm taking in fact the norm 2 because this is the 0 in n dash. Okay, and norm of the 0 element is 0 always. Okay, norm of the 0 element is 0. So if you take a positive number, if you take a positive number, right, you have norm 0 of x is equal to 0. Okay, is equal to norm 0. Right, is equal to norm 0 is equal to 0. This is less than m. Okay. What is the 0 image of any element x? For every x in n, you have this. Okay, if your x is coming from the vector space n, for the 0 image 0 of x, okay, you take norm. This is the 2 norm. Okay, and it is 0 of x is 0. Norm of 0 element is 0. Okay, and if you take m to be any positive number, you have 0 is less than m. So this is true for all x in n. Okay, for all x in this vector space, the norm of this is less than a positive constant. Okay, so you have this situation. Norm 0 of x is less than or equal to, in fact, you can as well write m into norm x. Okay, we'll show, see here, I am trying to define, to show that 0 of x is bounded. 0 of x is bounded. It is a bounded map, okay, because of this property. Because of this property, okay, because of this property, norm of 0 of x is less than m, we say this function 0x is bounded. Okay, if for any function, if for any linear map T of x, if you can show that you can find a positive constant or that norm Tx is less than or equal to m for all x in n, we say this T is bounded. Okay, that's what we mean by boundedness of any function. Okay, that is boundedness. And here we would like to define a boundedness of a linear map. We want to define bounded linear map. Okay, bounded linear map. Okay, if our map T is satisfies that norm Tx is less than or equal to m times norm x, we would like to call this function T is bounded linear map. Okay, if we have a linear map T, right? If we have a linear map T from n to n dash, and for that linear map T, if you can find a constant m positive, right, such that this is true for all x in m, we say that this linear map is bounded. Okay, that's what we mean by bounded linear map. And in fact, we'll show that this boundedness and this boundedness, these two are equivalent. In fact, we'll show that this is same as continuity. This definition of bounded linear map is the same as saying that this linear map is continuous on the whole of n. Okay, we'll show that these two concepts are equivalent, boundedness and continuity. Okay, that's how the phrase bounded linear map comes in. Okay, now I will enter the remark of the theorem 3. This is about the remark of the theorem 3.4.1 of the theorem 3.4.1. Okay, for Princeton people, we already taught this. Okay, and therefore I want to start off with this. For the others, I will come back to the important topics before this remark, maybe in the final sessions of this series. Okay, yeah, this is on page 63. This is on page 63. Okay, this remark is on page 63 of your course material. Yeah, what we do is this. Here we see. Now we are saying T is a map. T is a linear map from n to n dash, and then we know what we mean by bounded linear maps, linear transformations. Okay, And then we'd like to bring in a new function called norm T. Okay, we define this as the supremum of norm T of x such that norm x is less than or equal to 1. Okay. Yeah. Hello. Am I audible? Hello.
Yes, sir.
Okay. Okay. If you don't hear my voice, you please inform me. Okay. We'll bring in a new function called norm function. Okay. Norm on T. Okay. Where is T coming from? In fact, later on we'll define the space B of n dash. Okay. This is space of linear transformations, bounded linear transformations from n into n dash. We collect all bounded maps from n to n dash. Okay. From n to n dash. Right. Yeah. I gave you an example of a bounded map. In fact, I forgot to give you an example of an unbounded map also. I'll come to that. Okay. Yeah. So we'll in fact define this the set of bounded maps from the space n, linear space n into the linear space n dash. We can show that this is a linear the set of all bounded linear maps from n to n dash form a vector space. This is a vector space. Okay. We can show that sum of two linear maps is again linear, and sum of two bounded linear maps is again bounded. Okay. Yeah, that's how, and you can have vector space structure on this. Okay, that we prove later on. On that vector space, we can define a function norm by this. You can define a function like this and show that this is a norm. Okay, this also we do in the theorem in a few minutes. Okay, we define norm T to be the supremum of these norm of these image values. Is a mapping from n to n dash Tx. X is coming from x, this is x belongs to n. Okay, you have to take no, not normal. Okay, this is ordinary. You have to take x from n. Okay, this is this space, vector space n. You take x from n, you apply, and it says that norm x must be less than or equal to 1. Means in the normal space n, you are taking the points. Right, this is origin. This is origin. Okay, this is origin 0, right? And from 0 you collect all the points which are at a distance of 1 unit. Okay, and so the norm is distance. Norm is distance. Norm x is the distance of x from origin. Okay, right? You can simply call it d of x comma 0, right? Is norm x. Out of a norm, you can define a metric d of x comma 0. Okay. If you have two elements x comma y, you look at the difference x minus y, right? You consider norm of x minus y. That can be defined as d of x comma y. Out of a norm, and if you take two elements in x comma y in n, and if n is norm space, you can tuck off norm of x minus y. This can be defined as D, and you can see that this is a metric. This is called the norm-induced metric. On n, every normal linear space induces a metric. It is this. Okay, and if you substitute y equal to 0, you get this. Okay, x minus 0 is x, right? And this in fact is the distance. This in fact is the distance of x from origin. Okay, it is this. Right? If you take x here, let me use in the color. Right? Yeah, if you take x here, okay, if this is your x, this is d of x. This thing is d of x comma 0. Okay, it is norm x. It is norm x. The length of this segment is norm x. Okay, so norm x should be visualized as the distance between x and the origin. This is the origin in n. Okay, yeah, and you are taking norm x less than or equal to 1, and x are coming from n. So these are the points x whose distance from origin is 1. At the most, you are taking a sphere centered at origin of radius 1. Okay, so these are the elements x whose distance from the origin is less than or equal to 1. You can take the points on the sphere out, on the circle also. Even if it is circle, we call it sphere in a general setup. Okay, so in general, this is called a sphere, a closed sphere. This in fact is closed sphere, closed sphere, closed unit sphere. This is closed unit sphere. It is closed sphere centered at origin of radius 1 unit. Okay. For those x, you are studying the norm of the T images. Okay. T of x are coming from n dash. Okay. And yeah. So this is mapped to n dash. Okay. T maps. This is n dash. Right. T maps T. Right. T maps n to n dash into n dash. Okay. So T images. You may have as your x varies. So in this okay, in this closed sphere, T of x values may be varying. These are all they don't go out of n dash. They remain in n dash. Okay, because it is codomain. So these are all T of x dash. T of x values. If x is in here in the closed unit sphere in n, these are the T of x values. For all of them, you collect the norm values. It means here also you will have an origin. Okay, this is n dash is a vector space. So here you will have one origin. Okay, one origin will be that is the additive identity. In n dash you will have additive identity. From 0 you calculate these distances. Okay, these are the norms. This is T of x. This is T of x. You are calculating this length, that is norm Tx. That is norm Tx. The norm Tx is the distance of Tx from the origin, from the additive identity in n dash. So you are calculating all these distances. Okay. Out of them, you are taking the sum. You are taking the largest value of all these, or if where these are tending to, right? Where these norm values are tending to. That is sup value. That's how you define norm T. Okay. Yeah. Then we'll bring in three more constants. Norm T is defined as supremum of norm T of x such that x belongs to n. No. We use different color. X belongs to n, comma, x belongs to n, comma, norm x is less than or equal to 1. Okay. This is right. Norm T is defined with this. And then we consider, alpha is the sup of norm T of x such that x belongs to n and norm x is equal to 1. Okay, this is definition. We are considering this sup. I'm taking the points on the circle only. That is equality only. I'm taking. I'm not taking the points on this part inside of the circle. I'm taking the points on the circle only. So their norm values are ones. Okay. So on that circle we are letting x vary, and we are looking at the corresponding images, and for them we are taking this sup. Okay. That's for, and that this sup is defined as alpha, and then we define beta to the supremum of norm T of x by norm x such that x is in n and x is non-zero. Okay. You are having norm x in the denominator. It is a positive. This is a non-negative real number. Okay. We want this is not zero. Okay. To have that, we impose this condition. If x is non-zero, this is strictly positive because we are dealing with norm. Okay. And here I must try and the two line segments. Okay. The norm of this thing. Okay. The norm of the T image of this. This is the norm. This is the norm in the n dash space. This is the norm in the n space. Okay. Yeah. And we define gamma to be infimum of m positive such that norm T of x is less than or equal to m times norm x. Okay. Norm x is less than or equal to 1, or yeah, for all x. You can take all x for all x in n. Okay. For all x in n, you consider this. This speaks about the positive constant m for which norm to x is less than m times norm x means you are starting with a bounded linear map. So there will be a positive constant m such that it satisfies this for all x in n, and for all such m's you take the infimum that is defined to be gamma. Now we'll show that norm t is equal to alpha is equal to beta is equal to gamma. This is what we intend to prove now. Okay. Now you observe one thing. This is this set, right? These values norm x. So these values x belonging to n such that norm x is equal to 1, right? This is a subset of x belong to n such that norm x is less than or equal to 1. Okay. Why? These are the points in the closed sphere, right? This is origin, right? These are the points in the closed sphere, right? If you take a point here, its norm value is 1. I'm taking a circle of radius 1 unit. Okay, so if you take a point here, the distances from x are less than 1. Okay, and if you take points on this circle, their norm values are 1. Okay, so these x values form the points on this circle. Okay, so then these points are on the circle or perimeter or circumference, and these points may be lying on the circle or maybe lying inside the circle also. Right? These may come from the interior or on the boundary. Okay, and in fact, this is a subset. This is a subset of this. This is a subset of this. Right? This is a subset of this. In fact, if you have any element other than 0, and if you have elements x as that norm x is less than 1, this is larger. This will be larger. If you can get one x for which norm x is between 0 and 1, if you can get one x which is between norm x, if you can get one x in n for which it is between 0 and 1, this is strictly larger than this. In general, this is a subset of this. So therefore, the supremum of this will be less than or equal to supremum of this. Okay, right? Why? See, for example, if you take two sets 1, 2, 3, and if you take 1, 2, 3, 5, this is a subset of this. The supremum of this is 3. The sup of this is 5, and 5 is strictly less than this. Okay, right? Even if you take infinite sets, if A is contained in B, even if A and B are infinite, you can show that sup A will be less than or equal to sup B. Okay, this you can prove. Right? If A is a subset of B, you can show that sup A is less than or equal to sup B. Right? Yeah. That's how you have this is alpha. Supremum of these values. Supremum of these values is alpha. So alpha is the supremum of these values. In fact, because of this, you are not taking sup for these values. You are taking sup of the norm of the image values. Okay, so let me correct this. Right? Yeah. You are considering the same t of x, the same functional values here. Norm tx, you are considering norm tx for these x values. That is why supremum of norm tx will be norm tx, norm tx, norm tx, norm tx, right? For these x values, right? For these x values, I mean, x belongs to n and then norm x is equal to 1. This will be less than or equal to norm tx, such that x belongs to n and norm x is less than or equal to 1. Okay? So because this is subset of this, and for the same functional, you are considering the sup value. You are looking at the t images, and for them, you are taking the norms. Because of that, the sup of these values will be less than or equal to sup of this. Okay, so means you have this is nothing but is alpha. Okay, this is norm T. So you have now alpha is less than norm T. Okay. So that's how you have norm T is less than greater than or equal to alpha. Okay. You have alpha is less than or equal to norm T. Okay. I can say norm T is greater than or equal to alpha. Right. So you have this. In fact, I would like to show alpha is beta, and I'll show this is greater than or equal to gamma, and this is greater than or equal to norm T. This is how we obtain. Okay. We'll try to show alpha is equal to beta. This we showed. We'll show alpha is beta and beta is greater than or equal to alpha, and gamma is beta is greater than or equal to gamma, and gamma is greater than or equal to norm T. Means between norm T, these three values are lying. Means all of these will be becoming equal. Norm alpha, no, not norm alpha, norm T. Norm T, yeah, is equal to alpha, equal to beta, is equal to gamma. Okay, so let us obtain these three inequalities. Right? You observe this. Yeah, we look at alpha and beta. Look at alpha and beta, right? Yeah. See, we'll show these two sets are same. We'll show these two sets are same, right? We'll show these two sets are same. Let us see, right? Sup is defined for these two sets. Okay, we'll show that these two sets are same as sets. Okay, so let's do it. We are considering alpha beta is equal to supremum of T of x by norm x, as that x belongs to n and x is non-zero, right? And then alpha. Yeah, what is alpha? Alpha is equal to supremum of norm. Here you should go for norm. Sorry. Yeah. Norm T of x such that x belongs to n and norm x is equal to 1 is alpha. Yeah, is equal to 1. Okay, this is how we define, right? Right? We define beta to be this and alpha to be this. In fact, we'll show these two sets are equal. Let us see. Let us take this. This instead of x, I will take y. You can take any element. You can take x dash. It's a matter of notation. T of x dash. How's that? X dash belongs to n and norm x dash is equal to 1. Okay. I'm taking this set. In place of x, I'm writing x dash. You can write anything you like. Okay. We'll show that this is equal to this one. Norm T of x by norm x. As that x belongs to n and x is non-zero. Okay. I'm taking this set. Norm of T of x by norm x. As that x belongs to n, x is non-zero. I'll show this. Okay. You take an element here. So for elements here, you have norm x dash equal to 1. So here x dash can be written as x dash by norm x dash. Okay. X dash is x dash by 1. X dash is x dash by 1. Okay. This scalar 1 by 1 is scalar. 1 by 1 into x dash is written as x dash by 1. Okay. So and norm x, I am taking element from here, x dash. So and I have norm x dash equal to 1. Okay. So this can be written as what? Norm T of x dash, right? For x dash, I can write this. This is norm T. If in place of x dash, I can write x dash by norm x dash. Okay. So the elements here are of this form. These elements are of this form, right? In place of x, I can take x dash. Okay. If right, a norm x dash is a number. X dash is an element in n. So this also will be an element in n. Okay. And if your x dash is not, because norm x dash is 1, x dash is non-zero. So your x dash by norm x dash will also be non-zero. Okay. Yeah, you want this only not to be non-zero, so this is non-zero. So, for this x dash, these values are present here. Okay, how about the converse? Let us take elements here. Okay, let us take an element here. Let us write this as y. Let us write this as y. Okay, so I'm taking an element from here. Okay, I'm writing this as y equal to x by norm x. Okay, what is the norm value of this? It is norm x by norm x, and this x value is non-zero. I'm taking an x from here. Okay, and I'm considering this x by norm x, and I'm calculating norm y value. Okay, so it is norm x by norm x, right? And x is non-zero, so I can cut off one by one. Yeah, right. I can cut off. I get one. So for this y, for this element, norm value is 1. So this can be written in this form for some x dash. In place of x dash, I can take y. Okay, so how about norm y? Norm y is 1. Does y belong to n? X belongs to n. Norm x is a positive number. Therefore, 1 by norm x into x is present in n. X is in n. So x by norm x is also in n. So these elements can be written in this form for this x dash value. For this x dash value means these values are contained in this. These elements are contained in this. These elements are contained in this. Therefore, if you take the sup values, these two will be same. Okay, that's how you will get this. These two sets are same, and the sup of this set will be the sup of this set. Therefore, you have alpha is equal to beta. Okay, yeah. So now let us settle this beta and gamma. Yeah. What is gamma? Gamma is infimum of m positive as that norm tx norm tx. Norm tx is less than or equal to m times norm x. Okay. Yeah. For all x in n. Okay, this is how we define gamma. It is infimum of all positive constants for which norm tx is less than or equal to norm x for all x in n. Okay, and what is beta? I want to show beta is greater than or equal to gamma. What is beta? Beta is defined to be supremum of t of x by norm x. As that the norm of this as that x belongs to n and x is non-zero. Okay. Yeah. We now yeah. From here, this is because this is supremum. This is a greater than or equal to each of these values. So norm t of x by norm x. Okay, and if you take one m value, what happens? You have norm tx is greater than or equal to m times norm x. Right, for all x in n. If you take one m value, you have this. Okay, you bring you bring x to this side. You bring norm x to this side. What happens? This is norm t of x by norm x is greater than or equal to m. Right? This can be written as, right? I'm bringing norm x to this side. Okay, I assume x is non-zero. Okay, and then this is you can absorb this in this. This is norm t of x by norm x is greater than m. Okay, so if you take one m value from here, you can show that for any x value here, this is greater than that m. Okay, if you take one m value here, you can show that for each particular value t, it is greater than that this m. Okay, so and if you take infimum, this gives, if you go for infimum, so you have beta is greater than m. So if you go for infimum for all this, you will have beta is greater than or equal to m. Gamma. Beta is greater than or equal to infimum, which is gamma. Okay, it is greater than or equal to infimum. Yeah. Infimum of m's, this is gamma. Okay. Now beta is greater than m. Now you let this m vary. On the right hand side, you take infimum. So beta is greater than or equal to infimum. When you go for infimum, you should have equality. Okay, because it's a kind of limit. So in the limiting case, you may have equality. So that's how you greater than or equal to gamma c. And this is gamma. So that's how you have beta is greater than or equal to gamma. Okay. Previously you showed norm t is equal to alpha is equal to beta is greater than or equal to alpha and is equal to beta is greater than or equal to gamma. Okay. Now norm t is greater than or equal to alpha is equal to beta is greater than or equal to gamma. This we prove. Now we prove that gamma is greater than or equal to norm t. Right? So we already proved norm t is greater than or equal to alpha is equal to beta is greater than or equal to gamma. Okay. Now we'll prove this is greater than or equal to norm t. Okay. This remains. What is norm t? Norm t is supremum of norm t of x such that x belongs to n and norm x is less than or equal to 1. This is how we define. Okay. Norm t is defined to be this. Now, individually you take an element from here. Okay. What is gamma? Gamma is infimum of m positive such that norm t of x is less than or equal to m times norm x for all x in n. Okay. This is how we defined gamma. Okay. If you take these elements, can I do that? Yeah. If norm tx, yeah, for these values, can I show? So I have, I want to show, right, okay. For these values, what happens? Norm tx is less than or equal to m norm x. If I take element, right, if I take one m positive, I have this, okay, for all x. Okay. And in particular, for norm x less than or equal to 1, what happens? If I take the elements x in the closed linear disk, what happens? Norm t of x is less than or equal to m. Norm x is less than or equal to 1, multiply on both sides by m. You have m into this is less than or equal to m. M into norm x is less than or equal to m. Okay? Multiply both sides by m because m is positive. It does not disturb this. So m into norm x is less than or equal to m. So you have norm tx is less than or equal to m. Now you take supremum of all these. For these x values, in x in the closed linear disk, you take sup of all this. Okay, sup of all this. It has to be less than or equal to m. Okay, I am taking one m value. For that one m value, I am able to do this. And if you let this m values vary and among all those such m values, you take infimum. So that implies sup of norm tx is less than or equal to infimum is less than or equal to infimum of m's. Okay. Now this m can be anything from here. Okay, from here. So among all, so you'll have now among all of them you take infimum. Then you will have sup of all of this is less than or equal to infimum of all of m's. So this is gamma. This is your gamma, and this is your norm t. That's how you have this. Okay, gamma is greater than or equal to norm t. Okay, that's how you have norm t is greater than or equal to alpha, equal to beta is greater than or equal to gamma is greater than norm t. So this implies all these four are equal. Okay, so you, yeah. So we have not right. Yeah. So all these four quantities are equal. Okay. From here, we define this kind of functions to be bounded linear maps. If your linear map is linear map T satisfies this, we call it a bounded linear map. Okay. Yeah. And you can see theorem 3.4.1 that is equivalent to continuity. Boundedness is equivalent to continuity. That's how bounded linear maps will be equivalent to continuous linear maps. Okay. For such continuous linear maps, norm T can be calculated by any of these 4 values. Okay, this is norm T, alpha, beta, gamma. Any of these 4 values are equal. All these 4 values are equal. You can calculate any one of these depending on the comfort in computation. Okay, yeah. Now let's move to the next theorem. What is it about? It speaks about linearity of T inverse. Okay. Yeah. Say you have a map T from N to N dash. Okay. And say this is onto. If I write 2 arrows, it means it is on. Okay. If it is 1 to 1, whether it is, yeah, with ontoness, you can define T inverse. What is T inverse of a Y? It is set of all x in N such that T of x is equal to Y. Okay. You have, this is N and this is N dash, right? And this T is mapping N into N dash. It is taking x, to Y. Okay. It may take some x1 also to Y. I'm not asking for one-to-oneness. So you may have different x values. It may take x2 also to Y. Okay. Unless if your function T is 1-to-1, then there will be a single preimage which is taken to Y. Okay. In general, this is the inverse image of singleton Y. For Y, inverse image is what? You collect all x values for which these x are coming from N, for which T of x equal to Y. These are the preimages. These are the preimages of this element. Okay. That's what we mean by T inverse Y. Okay. Yeah. Now, if you define like this, then or if you go for T 1-to-1 also, T N maps to N dash. Say it is onto and 1-to-1. Okay. Then let us show that T is linear if and only T inverse is so. Okay. If your T is linear, if your T is mapping N to N dash, okay, and if it is 1-1 and onto, if this T is 1-1 and onto, and you can show that your T inverse is also 1-1 and onto. Okay. Yeah. Let us assume this and show this. Okay. So to show this, you have to take elements from here. You take T inverse, right? You take elements from W1, W2 belonging to N dash. Okay. And you consider CW1 plus W2. Right? You take elements of W1, W2 belonging to N dash and look at the T inverse image of this point. Okay. Now, because I'm assuming T inverse here, T is onto, there will be elements x1 which is taken to W1. There will be element x2 which is taken to W2. Okay. So this can be written as T inverse of C times W1 can be written as T of x1 and then plus W2 can be written as T of x2. Okay. W1 is the T image of x1. W2 is T image of x2. Okay. For W2 I have written T of x2. Now this is T inverse of, you can bring C inside because your T is linear. This is T of C times x1. And again, because your T is linear, T of x1 plus T of x2 is T times x1 plus x2. That's how x2 comes inside. Okay. So this is the T image of C of x1 plus x2. Now I'm assuming T is 1-1 and onto. Okay. I'm assuming T is 1-1 and onto. T is 1-1 and onto. Okay. So T inverse of T will be identity of C of x1 plus x2. So this is nothing but C of x1 plus x2. And T of x is x. Okay. That's how. That's what is x1? X1 is T inverse of W1 plus x2 is what? X1 is what? The T inverse image of W1. X2 is what? The T inverse image of W2. Okay. That's how. Your T inverse of C W1 W plus W2 is C times T inverse W1 plus T times T inverse W2. T inverse of C W1 W2 is C times T inverse W1 plus T inverse W2. Therefore, T inverse is linear. Okay, you can prove the converse. If you assume this, you can prove this. Okay. By the way, here we came across identity. This identity transformation is an unbounded linear transformation. This is an unbounded linear transformations, right? I said I'll give you an example of unbounded linear map. Identity map is one such. It is an unbounded linear map. Okay. Yeah. Now you have this theorem. Right? Let T map into n dash be onto. I assume n dash are linear maps. Okay. I assume T is linear map, n and n dash are vector spaces. Okay. And I also assume T is onto. Okay. Then we have this. Then T is 1 to 1 and what? I forgot. Oh, before that I have the theorem. Okay, right. And T inverse is bounded. Yeah, the same theorem I'm talking about. T inverse is bounded, right? In the exam, you have to write fully, if and only. There is a positive constant m. There is m greater than 0, such that m times norm x is less than or equal to norm tx for all x in n. Okay? Yeah. Let n and n dash be normal linear spaces and T be a linear map onto, and that this be linear in a map. Okay? And then T is 1 to 1 and T inverse is bounded if and only if this happens. Okay? Let us prove this. Okay. Let us prove this. I start with this part. Let me assume T is 1 to 1 and T inverse is bounded. I'll obtain this. Okay? Yeah. See, you may recall what do we mean by boundedness? What is meant by the boundedness of T? Norm Tx is less than or equal to Bm times norm x. Right? By T is bounded, we mean this. Okay? We mean this. But here, see, this is a lower bound on norm Tx. On norm Tx, this is a lower bound. Okay? Here, if you bring m to this side, right? No. Yeah, you retain m here. On non-Tx, this is an upper bound. That's the difference. This is a lower bound on non-Tx. This is an upper bound on non-Tx. Okay, that is the difference. Because we are speaking of a T inverse. Okay, that this change is taking place. Okay, now let us come to this part. Yeah, let T be 1 to 1 and T inverse be bounded. Okay, what is meant by this? What is the boundedness of T? Previously we said norm T of x is less than or equal to norm m greater than is less than or equal to yeah. See, here we have this is less than or equal to m into norm x. Okay, this is true for all such m. That right? If you have a for when T right. Okay. Now, if your m is bounded, you have to obtain this. If your T is bounded, you have to, I'm sorry. If your T is bounded, you have to obtain this. Similarly, if your T inverse is bounded, in place of T, you must obtain a similar kind of this. Because your T inverse is acting on this. T inverse acts on some W here. And you should have, it is less than m times some norm W here. Okay, let us see. T inverse is bounded. Means what? And let us replace this. For every W here, for every W belonging to N dash, right? Norm T inverse W will be less than or equal to m times norm, right? Here I must take W. Okay. Here, this is the condition for when T is bounded. If your T is bounded, that's what we mean. This is what we mean by T is bounded. Okay. You replace this by in the term. You replace this in. You convert this in the terms of T inverse. So T of X is of this. You will come T inverse. Where does T inverse act? It acts on W because T inverse acts on N dash. Okay. T acts on this, and T inverse maps N right on N dash and takes N dash into N. So T inverse acts on this, and you take an element W here. So non-T inverse of W will be less than or equal to a positive constant M times right. There exists an M positive. Okay, and here comes what this point. This premise comes. Okay, this is from the definition of T is bounded. Okay, because our T inverse is bounded, we can write like this. Now, let me erase this. Now, what our T is 1, 1 on 2. So there, because W is in N dash, there exists an X in N dash such that there exists an X in N such that T of X is W. Okay, if you take a W here, there will be an X in N such that this X is mapped to W. Okay, but this W becomes image of pre-image X. Because this happens because your T is on 2. Otherwise, it may not be possible. You are taking MW from N dash, so there will be an X in N such that T of X is W. Okay. Now you put T of X for W. What happens? Norm of T inverse of T of X is equal to, what is this equal to? X. Because your T and T inverse are inverse of each other. Okay. And you are assuming 1 to 1 also. So T is a bijection. So T inverse T will be T inverse composite T will be identity. Identity of X is X. So this is norm X. This is less than or equal to M times. Here comes in place of W, you are taking T of X. Okay. And yeah, to bring 1 by M to, you bring M to this side. Okay. So that gives what? So if you bring 1 by M to this side, this is 1 by M into norm X. Okay, I'm bringing 1 by M to this side. It becomes 1 by M into norm X is less than or equal to, right, norm Tx. Okay, so in place of a small m, you take 1 by big M. M is positive. You can speak of its reciprocal. So in place of small m, you can take 1 by M. Norm X is less than norm Tx. Okay, this is true for all X in N. For all X non-zero, this is true. Okay, for X 0, you can easily calculate. Okay, if your X is 0, norm 0 will be 0, and T of 0 is 0, you will have equality here. Okay, that's how this implies this. That's how this implies this. Okay, let us look at the converse. So this part. I'm not writing some sentences, okay, to save time, but in exam you have to write each and everything. Okay, now let's look at this part. So T inverse is bounded and T is 1 to 1. T is 1 to 1 is equivalent to that norm Tx. No, is equivalent to that. There exists M positive. No. There exists M positive. There exists a small M positive such that M times norm X is less than or equal to norm Tx. Okay. We put this simple as this. I want to assume this and obtain this. So let there exists small m positive such that norm, this is true for all X in N or all X in N. Okay. Yeah. So let there be a positive M such that M norm X is less than or equal to norm Tx for all X in N. Okay, let me assume this and I'll obtain this. Okay, to obtain 1-to-1ness, so to obtain 1-to-1ness, you assume images are same. Let T of X be X1 be X2 for some X1, X2 coming from N. Two elements X1, X2 in N, assume their images are same. If we can obtain X1 equal to X2, then T becomes 1 to 1. What does this mean? Because our T is linear, you bring T of x to the other side. T of x1 minus T of x2 is 0. Okay? Because your T is linear, you can write this as T of, okay, T is linear. T of x1 minus x2. Okay? So you can write this as T of x1 minus x2. Now, T of 0 is always 0. For linear maps, you can prove this. So T of 0 is 0. And your T is 1 to 1. Yeah. T of 0 is 0. Yeah. So what happens? You look at this. You look at this. You don't go for this. Now, you put x1 minus x2 for x here. What happens? Now, m times norm x1 minus x2 is less than or equal to norm T of x1 minus x2. Okay, it is x1 minus x2. I'm writing x1 minus x2 in place of x in this. Okay, now this is 0. T of this is 0. This is norm 0 is 0. Okay, and m is positive constant. Therefore, this implies your norm x1 minus x2 is 0. Okay, this has to be 0. This cannot be a positive number. This has to be 0. Means what? And then because you have norm here, you must have x1 minus x2 equal to 0. This implies x1 equal to x2. Okay, so you showed this and could obtain x1 is the previous are same. Therefore, your T is 1, 1. Therefore, your T is 1 to 1. Okay, this we obtain. Now it remains to obtain this. Okay, yeah. So what we have, there exists a small m positive such that m times norm x is less than or equal to norm T of x for all x in n. Okay, to show T inverse is bounded. Right? Yeah. What should happen for T inverse to be bounded? We should have there exists a capital M positive such that norm T inverse of W should be less than or equal to M times norm W for all W coming from n dash. Okay. Yeah. To show T inverse is bounded, we should be able to produce an M positive constant such that this happens. Okay. Now, because our W is right, our T is mapping n to n dash. Okay, and your T is on to 1 to 1 also. It is one. We showed it is 1 to 1 also. So we can speak of you are taking W from here. We can speak of its pre-image. Okay, there will be an axis here which is taken to this. Why? Because our function T is on to. Since W is in n dash, there exists an x in n such that T of x equal to W. Since T is on to. Okay, because T is a surjection. For W in this, there will be pre-image which is taken to W. Okay, now for W substitute this. Now you have in this for x you substitute this one. From here, what do you get? For here, from here, what do you get? X equal to, this implies x equal to T inverse W. Because our T is 1 to 1, you can speak of T inverse W. That will be x only. Okay. Now for x, you can take TW here, T inverse W here. Okay. So one implies m times norm T inverse W is less than or equal to, what is T of x? W. Okay. Now you want this m onto this side. You compare these two, this one and this one. This m is small m is extra. Take it to the other side. Assume, your m is positive, so you can take it to the other side. So it is norm T inverse of W is less than or equal to 1 times m into norm W. Okay. This plays the role of this big M. Right? You can take small m to be reciprocal of small m to be big M. So now this is of this form. This, right? If you take big M for 1 by M, you take big M for 1 by M. So right, then you have this inequality is of this form. Okay, so that's how we obtain that. This implies T is 1 to 1 and T inverse is bounded. Okay, so for linear maps which are surjections, 1 to 1ness and boundedness together give this, right? Give this, yeah. And means you have to put in mind that right? Yeah. Okay. This is the other side of this one. Norm Tx is less than or equal to big M times norm x. Okay. When T is bounded, you have this. In fact, you can replace M by norm T. Okay. Because you are taking in form of all this, norm T of x will be less than or equal to norm T norm x. Okay. And this speaks about the upper bound of norm Tx. This speaks about the lower bound of norm Tx. Okay, that should be kept in mind. In fact, when you compare the normal linear spaces, okay. For example, in fact, when you compare in Rn, if you compare two norms, this kind of inequalities help you to compare two norms, equivalence of two norms. Okay, yeah. So that's about the theorem. Can we further move? Yeah, that is theorem 3.4.3. Okay, theorem 3.4.3. Okay, let n comma n dash be normed linear spaces. I don't tease this, but I try to brief it. Okay, let n dash be normal spaces, normal vector spaces. Then then you consider beta of n comma n dash be the set of all continuous bounded continuous linear maps. Continuous or bounded, both are equivalent. Continuous linear maps are transformations from n into n dash. Okay. Then B of n comma n dash is a linear space. Is a linear space, right? B of n dash is a linear space. Tell slowly. If I don't say, like with high voice, nothing comes out of my mind. I am addicted. Slowly, slow. See, I'm very slow. I'm going very slow, right? If I go further slow, I'm afraid what I can complete. Okay. Right. Then B of n and dash is a linear space. Okay. Then B of n and dash is a linear space. Define norm T equal to supremum of norm T of x such that x belongs to n and norm x is less than or equal to 1. You define norm like this, then you can show this is a norm. Define this. Then this is a norm on B of n and dash. Okay, right? If n dash is complete, so is B of n and dash. Okay, so here we are taking two vector spaces n and n dash. And we collect all bounded linear transformations from n into n dash. Okay. For linear maps, boundedness is same as continuity. Continuity means for convergent sequences, image sequences are also becomes continuous. If mapping T from n to n dash is continuous, n to n dash, a mapping T from n to n dash is continuous, you take an element x from here and you take a sequence x and converge it to x. T of xn must converge to T of x. Okay, that's what you mean by continuity. If T is a linear map from n to n dash, for every sequence xn converging to x in the norm, T of xn must converge to T of x. Okay, for linear maps, boundedness and continuity are equivalent. Okay, so you collect all linear maps from n into n dash, denoted by this symbol. You can show that it is a vector space. If you add, you define point-wise operations, you can show that sum of two linear maps is again linear, and a constant of linear map is again a linear map. Okay, you can show that all such linear maps, all this kind of linear maps form a vector space. On that vector space, you can define a norm like this. If you define like this, for each T of x, for each T, you can define norm T, right? So you can show that this is a norm on this vector space. Okay. In fact, if your space n dash is complete, you can show that this also is complete. What do you mean by completeness? If every Cauchy sequence converges, if in a space every Cauchy sequence converges, we say that space is complete. Okay, so you take a Cauchy sequence in this space under this norm. You take a Cauchy sequence. If right, you can show that that Cauchy sequence converges. This becomes complete. Okay, yeah. Here I want to stop because I am exhausted, and you people, if you are attending since morning, definitely you would have been exhausted. Okay, I would like to stop here. Any doubts you want to ask? Hello. Hello, is anybody there? Hello.
Sir.
There?
ఈ నోట్స్ అంతా రాసుకోలేదు, కొంత నోట్స్ దీన్ని పెడతారా సార్?
What?
అంతా notes, I could not write all the notes.
No, sir. I cannot give notes.
No, sir.
Because this is recorded. No, like while I'm teaching, you should be able to note down. I don't prepare separate notes.
Sir, okay. But it is recorded. I can back down and.
Yeah, you have to prepare your own notes. Okay.
Okay, sir.
Anything else?
Sir, is it first chapter, third chapter to started, sir?
Huh?
Is this third chapter to started?
I'm not
third
getting.
Chapter to, this is functional analysis. Third chapter to started. Starting onwards means normal linear space.
No. I am today. I spoke from third unit. Everything is there.
Okay,
First 2 units are also there for exam. Okay, for the principles people, I covered the previous portion. Okay, yesterday I was speaking on linear vector spaces and norm. Okay.
Yes, sir. Yesterday we did not get, sir. That's why I'm asking that.
What can I do? Okay. So please look into the recording. Okay. So today I started from that portion. In the final 2-3 session, I will come back. I would like to come back to first 2 units. Okay. That's what I am planning.
Okay.
Anything else?
Thank you.
Okay. Anything else? Are you able to follow me?
Yes, sir.
Are you able to understand what I am saying?
Yes, sir. Yes, sir.
Okay. I'll stop here. Right. Thank you.
Thank you, sir.
Goodbye.